So, Project Loon. We're going to just be skimming through some of this stuff today. Just looking for some interesting tidbits, maybe collecting them for future tweets to explore. We looked at the big PDF last time. Feel free to ask questions and talk about it. Anything's up for grabs. This is a casual stream today, so let's hang out. Talk balloons. And or life. Okay, the Loon Collection is a compilation of lessons, data, and insights from nearly a decade of stratospheric exploration. It includes the Loon Library and flight data from nearly 2,100 flights, including sensor data and electrical measurements, ranging from the first flight experiments in 2011 to the final flight in May 2021. We hope these resources will inform and inspire future explorations in the skies and keep stratospheric research and innovation aloft. That's nice. I started on the project in February or May of 2012, so I came on very early, and I stayed till 2017. So yeah, technical stuff. We looked at this, which is a PDF, and so let's look down at the supplementals. How are you doing today, Steve? And everyone feel free to say hi in the chat.
Great.
Nice. I think I got the hour wrong for you guys down there, or over there, didn't I? Okay, so are there any votes on which of these to...
Last time, yeah.
Yeah. Which of these to take a look at first? What's the dinging? Yeah, okay. What do you think about that? I'm gonna get myself a Soylent Food Nutritious lunch. Fine beverage. It is the consistency and the taste of pancake batter. I'm not sure if you guys have pancakes over there in the UK by that name. Reliability, that's kind of dry. It's very dry.
The schematic is kind of fun.
All right, let's peek. Schematic it is. Loon schematic. Ooh, kind of detailed. I mean, by kind of detailed, it's not a schematic. It's a block diagram, but you get some info. Schematics would actually have been most important because there's some techniques that were super valuable and necessary in the electronics.
Interesting to see how it evolved.
Oh, I didn't even know there was an evolution in this. Yeah, there's one technique that's very important. I guess it's kind of common, but for every single line that goes off of a board, you have to put lightning protection on it. And RF noise suppression, like every single line. The power lines, the ground lines, the data lines, your sensor lines. And there's a particular network of passives that Loon used as cookie cutter for the edge of the board. Looked like you stamped the circuit design all around it. But that's easy to reproduce, and sometime I will have to reproduce it for you. Super handy. I doubt the Pico balloons, I think they'll probably have bigger problems than a electrostatic discharge if they're next to a storm. Okay, so let's start at the middle, shall we, rather than the top. What is here? So mother brain is the... hard to zoom into. I think this is the main mother brain power. You see, I wasn't actually involved much in the electronics, so this is kind of interesting to me too. So the PFC, oh my goodness, zoom, you're not behaving. PFC here, primary flight controller, which we actually called Major Tom, or its flight software was called Major Tom, in a nod to David Bowie's Ground Control to Major Tom song. So Iridium was the flight command and control system, Iridium SBD. Loon used the Iridium 9603 modem, which is super common these days in trackers and hunting messengers. So there was Ethernet by the end. There certainly wasn't in the beginning. There wasn't where does that USB go? Yeah, okay, so debug. Yes, that was there all the time. Just a serial USB port to log in via a console text console. There's your GPS, the Iridium Ethernet. So the Ethernets were added late in the program, usually to talk to the cell phone stuff, the radio stuff. Payload CAN, PPS data over LVDS. CAN was very important. The CAN bus, which came from the auto industry, is good for long lines, long runs, and that went from the payload down on the bottom, and it went on a cable that wrapped all the way around the balloon to the top, where our flight termination system was to communicate with the Apex board, which we'll look at sometime. LVDS, low voltage data signals, PPS, that would just be a time signal. I'm not sure what we had LVDS going to, but maybe this green line will show us. Drew down, green. Where are you going, green? You're going to a cylinder, which goes to bottom left bulkhead. That's very specific. Which then keeps going to another cylinder. And the ADS-B receiver, power port 2. Wait. See, I'm not familiar with that. That was a later add-on. Gonzo. I always hated that name. Oh yeah, this is the old one. Let me take a look at the legend. The Wi-Fi. I think that was that very old? I should have taken a look at the legend first. Oh yeah, that's new stuff there. So many things. It'll take hours to go through this. We probably won't do that this time, all of it. But I'll note to do that on a future stream. Yeah, I could tell you so many things about every one of these blocks. We'll do that. No forward junctions, color codes, cables, squibs. Oh, squibs are fun. With one bang, you can sever anything that's 3 millimeters or smaller. Like Loon used these little pyro cutters.
What are the squibs used for?
So the squibs were used to sever release pins on the very top of the balloon. And I should set up my iPad for screen sharing to draw on. Maybe I'll do that later in a break here. I can just draw on the screen and hold it up for you. I love the Apple Pencil, by the way. I'll make you a diagram. So at the top of the balloon was a flat round plate about 60 centimeters in diameter, and on that plate was a couple windows into the balloon, and those windows were just covered with standard balloon film, polyethylene basically, and they were half semicircle shaped, like crescent shaped, and the way they would end the flight was to actually, sorry, I'm losing my focus. It was to actually cut the window open, so the helium would push the flap of plastic up, and the helium would all rush out through the hole, and that would remove the lift, and the balloon would start descending. And that cutter that zips around the edge has to be super reliable, because it is often a safety thing for termination to happen when you need it. Like you might be going into a country that doesn't want you. You might be approaching an airspace that doesn't want you, or you might be about to cross like a population center you're not supposed to cross, or even you might want to do it before your balloon blows out to sea if you know it's on its last legs. So let me open the drawing app here. Let's see if I have power in the pencil. Go to my balloon. Can I screen share? I can. I can screen share. Holy crap. I happen to know how to do this. You're gonna love this. I'm gonna love this. It's really easy. When you have an iOS device, you connect the USB cable to the device and you open, of all things, QuickTime Player. Weird, right? Very weird. And you do a new movie recording, again, random. And you change the source. Oh, here, I'll just show you. I'll add this window and you can see me change the source. Oh, this is gonna be fun. New window capture. Add iOS QuickTime. Okay. Window QuickTime Player movie recording. Okay. I'll just switch between these two as we like. Oh, that's the wrong shape, but I'll show you. So you click on this little caret. Oh, it doesn't show up. But you click on that little down arrow, and a menu shows up, and your iOS device is in the list. Take a look at that. Is that not fucking cool? Tell me that's not fucking cool. Now I gotta reshape this window so you can see the right bits, the good bits.
PyChamp.
I'm gonna assume that means good. Right? Does that mean good? I'm a little behind in some of the slang these days. I'm catching up on Twitch. Oh gosh, this iPad's huge. 9:41. Oh, this is displaying like the stock standard time. That's the time all the Apple events show on iOS devices. Okay. Sweet. Do I have Apple Pencil power? I do. 35%. Okay. Let's go look at this awesome drawing app. Oh, I'm so excited. I can share this with you guys. Let's do a new project. Stream. Sharing. There we go. Beautiful. I really have liked this program for just engineering, like napkin sketch drawings. Let me lower this mic so you can see me a little better. Why it's so high in the window today. Okay, so let me bump our size up a hair here. Okay, so what we had was sorry, bear with me, it's been a little bit since I've done the drawing of stuff guide. Can we get a circle? Ellipse. Yeah, it looks a little weird, but close enough, right? Close enough. Okay, so we had, basically it was a plate that had concentric rings, and a bunch of little bolts around here for all of the tendons which ran down the valleys of the balloon cores to attach to. Those tendons would go radially out like this. This is so much fun. And so forth on around there. It's dinging on my wrist. Oh, just signal chat. Can you guys see this okay? By the way, Boogeyman, I'm getting to the squib. This is part of the explanation about what the squib was for. Okay, so guide, ellipse, arc.
Yeah, we can see it. Great.
Excellent. This is amazing. Undo. There's one arc and line there. Snap options. Autocomplete. Let's just see if we can. Oh, that didn't work, but close enough. You get the. I'll just do it. We'll do smoothing at 100%, which will give me a straight line. Go, and we'll slice that out of there. Where's my tool selector? I want to do a slice. So we'll slice this here. And we'll do a little, undo that. Do a little arc here with my shaky hand. And so this was the shape of the plastic window in the plate. It was a solid metal plate. I should just give you a little idea of this. Let's take this into blue. Change that to watercolors. Brushes. Watercolor. So yeah. I'm forgetting how to, relearning how to use my tools here. So this is all window. So that's all the window there. The rest was white powder-coated steel for strength, because the actual, like, the tension across, like, from here to here, that's not useful. Like, the tension across here to here between the ropes was 1,000 pounds. 2,000 pounds. Each rope was is that right? No, 1,000 pounds. Each rope opposite of each other was in a tension of 1,000 pounds force. So it had to be steel. Anyway, so the what we had here was there was like an arm that went. Let's get ourselves a new color. So there was an arm that was here, and it went over here. And right at the end there, they had this blade, this cutter blade, and that was held up on a little ramp. So this it was held above the plastic there, and between that and what you see is the next thing here. So there was a little string between right here that went back here, and there was a metal pin, a metal pin here that the string was tied to, and around that string, around that pin, was this little tube with a little wire. And that tube, if you looked at the side of it, was like this. and there was a hole in it. And this hole was what that steel pin went through. And the squib has, in this area here, it's got a pyrotechnic explosive device. And that forces a little anvil, basically like a little pyramid-shaped thing that's right here inside. And it forces that thing to go up here, and it ends, it's all in this pipe, and it ends there. So anything that was in that hole will just get smashed through by this sharp wedge and just severed, including steel. It is a fucking powerful little device. And so that severs the steel pin, and that then, oops, I had everything in the layer. That then will cause this to, let's see here. How do I do that? I'll just do a yellow. That then causes this to travel like that. It rotates around this center point, and it basically cuts a slot, or cuts a path following that yellow, which then lets the blue flap open. So that is what the squib is used for. So I like that. I was able to really explain that much better visually. So that is the apex plate, and on top of the apex plate was a little circuit board that we saw in the diagram.
Very cool.
Yeah, I agree. So let's go back to the, let's turn iPad off. I'm excited for this possibility. I'm sorry to keep going on about that, but okay, so we'll come back to the schematic. Let's just do a quick look again. Because I will talk all day on all of these things, which is fun. Let me just make a note of this to come back. Loon dump notes to talk about. Schematic. Okay. Any high points? So yeah, we had a transponder on this, like an aircraft transponder. And that was so we showed up on air traffic control's screens. And that was a Trig brand transponder, one of their most expensive ones. Horribly expensive, like thousands of dollars each of those things. Iron Sky was a steel. I'm sorry, this zoom is not happy in Chrome. That was it was a hopper that had steel powder in it, and Iron Sky was able to use it was just an opener at the bottom. It would just open the valve and drop weight, drop mass, which solved the problem of losing helium. It's kind of a hack, and it causes your top altitude to raise, and also unfortunately your bottom altitude. As you drop mass and lose helium, you start getting higher and higher for your operational range, but it keeps the pressure up in your balloon, which is what is absolutely necessary to stay flying. A super pressure balloon must remain pressurized, or it falls out of the sky. Gently, but it's going to come down. Yeah, the valve and compressor, that was the altitude control system for the whole balloon. It pushed air into the ballonet in the envelope. Hey, folks! This little line of text was what I contributed to the flight. Every flight had my lift gas concentration sensor aboard, and that was in the ballonet, the air chamber, to detect if helium was leaking through into the air chamber. It worked magnificently. It was this tiny little thing, about an inch by an inch. It was actually an off-the-shelf Sensirion pressure sensor that we hacked with a few special I2C commands. So it would give us thermal conductivity data instead of pressure data. Okay, we'll come back to this another time. Any votes for the next thing to peek at?
Compressor has the power slip rings.
Yes, exactly. Oh my god. Oh my god. The slip rings. What a bastard. What a bastard. Okay, I gotta look at the slip rings, show you the slip rings, because those were the bane of the project to the end. You're running a 60,000 RPM motor. It's a turbo compressor. And what that means is you're running 70 amps at 50 volts through a slip ring. Oh my god. Boogeyman, if you're still here, you will appreciate this. It was absolute disastrous because the high current would cause arcing whenever there was any bit of dirt or whatever despin. And it would cause a little arc through any little bit of dirt, and it would make a little pit. So these are the wipers in the D-spin slip ring. You see a huge number of them to carry the current, as well as sensor data. Will they show the pitting? I thought they showed the other side of the slip ring problem. Let's type slip. Yeah. Slip ring. Slipstream. Slip. No. Okay, they don't show it. But anyway, you can see black marks all around the slip rings, and it caused, even on the data lines, it was happening. And I think that was actually because of, ESD and induced current jumping through those from storm discharges nearby. While all of the ends of the electronics were protected from induced current spikes, the slip ring couldn't be protected from that. So as we're going back to any votes for the next peak here. I'm so happy to be able to talk about this stuff, guys. I've been keeping it in my head, all the cool, interesting
Hydra
tidbits.
battery.
Hydra, here we come. Honestly, I wasn't excited to start the stream today, but once I get into it, it's good. I'm glad you guys are here. That's actually what makes the streams fun for me, is when there's people to talk to. Oh, it's a big dock. Well, not that big, just a big table of contents. So let's see, 3rd gen pack, 2nd gen. Oh, that's horrible. Sorry. Self-management electronics, custom firmware, off-the-shelf fuel gauges. Yeah, battery fuel gauge chips are not good for balloons, and that's because of the potential high temperature swings over time. You have difficulty doing state of charge estimation with large number of high current packs that are doing temperature swings. So we see management pack heat, and you have to have heaters in all of the battery cells, and you have to make sure that somehow you heat all the batteries evenly, because the amount of charge current you can apply to each battery is determined by its temperature. So you don't want cold cells and hot cells in one block that you're only measuring temperature in one spot for. That was actually a tricky problem. We had a thermal guy who was on that for a long time. Strip heater, that would be what I'm talking about. Major Tom. So yeah, here you go. It's a cool table. 50 volts was our the United States safety limit for DC current was 50 volts without being classified as high voltage, which puts you in a whole another category of protection measures required. So we had 11 watt hours per cell. That would be an 18650. I think they were all 18650s. So we had 12S 2P, mass 1.4 kilograms. Oh my God, Steve, you can see 1.4 kilograms in one pack. It's a lot. But specific energy, this is what really matters for balloon hours. It's power per kilogram. Is it power? Capacity? Whatever. Charging, discharging, 18650, yeah. Yep. Serves prismatic, shock. 150 Gs. Ew. Yeah, we actually experience 300 to 500 Gs when a balloon bursts. Can you believe that? 500 Gs are applied to the top attachment point for the payload. And that's because you had 48 ropes, and every rope was under 1,000 pounds of tension. So when one of them goes, what ends up happening is, when one side splits, what ends up happening is you have 24,000 pounds on one side, and all of a sudden all the ropes lose tension on this side. So you have 24,000 pounds of force applied to a metal ring all of a sudden in that direction. It's a very short time scale. I think maybe 1/10 of a second. And so all of a sudden acceleration is stupendous in that direction. Now it doesn't last long, because it only lasts as long as the ropes have the tension. So maybe another half second, quickly dropping off. But 500 Gs for half a second is it's pretty harsh. And they had to make a brake link, because we didn't know this initially, and our payloads were hard mounted to the bottom of the balloons, and with the burst, oftentimes the payload would just get ripped off, just fall separate from the balloon, which unfortunately the payload didn't have a parachute. So we would make little craters, and our payloads would come back half as high as when they left. No one talks about that, but thankfully it never happened to do any damage to anything on the ground other than probably sagebrush. They figured that out after a couple of years. Yep. This is not all that interesting. Heater, that could be interesting. Yeah, ambient -80 to +50. A resistive strip heater situated between the cells, and 3 temperature thermistor sensors. Yeah, see, 3 of them. Yeah. So when they say a resistive heater, that means they had a Kapton, not Kapton, Mylar? What do they call it? Flex circuit. Basically just a flex circuit with that they run high current through, and so the traces generate heat that would wrap around every battery in figure 8 pattern. Yep. Robust. Batteries remain always on, yet can be easily turned off by users as intended on the ground. Oh, interesting. They could pull up individual packs. That was definitely not there in the beginning. Huh. And you had to be able to turn off the whole thing in a terminal situation. Like when the thing lands finally, you don't want the solar panels still keeping everything alive on the ground for safety of people who find it. And also for the iridium data cost. Long-term sleep mode. Health assessment, cell protection. This would be interesting for designing batteries, but not so much for streams. Again, ask any questions that you like. Shipping shock detection. Shipping conditions, measuring what's happened to all the balloon components was a particular thing that I was frustrated that Loon didn't do for years and years, because some of this stuff is fragile, and there was just an assumption. There was just no concept that something would happen to it between the time they put it in the truck and the time they took it out of the truck. An onboard shock detector. Excellent. Good job, people. State of charge. Yeah, pretty classic battery management. Yep. Temperature. Exactly, yeah. As your temperature goes down, you can only extract a certain amount of energy. However, if you warm up, there's more energy left that you could extract. Kind of expands and contracts. Cell characterization. Be nice if they actually told us the model number and manufacturer of the cells, wouldn't it? I guess it'll show you what you want to look for in the market. I do happen to know the model and manufacturer if any of you actually want to know. We'll do that offline. Cool. Moving along. Next. Any next things? I didn't see anything tweetable to me in there. I think we'll look at target fill moles. That was actually my job there as well, was fill systems that controlled the number of moles we put
Photon
into the
Harvesting.
We'll go photon next. That's a mildly interesting topic. My boss Chad there designed all that. He was the thermal guy. It was interesting. By the way, PE01 was the last best balloon film that Loon used. Steve, we talked about this before. Data suggests that for most balloons, leak rate is not constant and increases linearly with time. Now, there's a differentiation here between leak rate and diffusion. This is not including the diffusion. Leak rates were always order of magnitude higher than diffusion, and we know that diffusion increases over time with the polymer chain scission that happens from UV photons, which come into the long chain polymer plastic and literally chop the long chains into smaller and smaller little chunks, and that actually opens up more space for the helium molecules to wiggle through. I guess atoms for that gas. And it's tricky to measure leakage over time because your pressure swings up and down every day based on temperature. And so you have to watch it for at least a week, and you have to know the air temperature outside and the gas temperature inside to get any level. Did I just lose my stream? No, the iPad went to sleep. Okay. Right. Okay. So anyway, estimating is good. Recommended fill moles per day. We'll go over this in detail. I keep forgetting we're gonna just skim here. This is good. We'll tweet about this. We'll go into another stream about this. Fill moles PDF. Yeah, so when they figured out the target, we filled them with an extra 4 times 170 moles of helium to compensate for extra leakage. So they would do all of that calculation and then give it to my machine, and it would just fill that amount at launch. Reverse.
One imagines big balloons are at an advantage because leakage and diffusion must be dependent on surface area, whereas total gas is a volume thing.
Absolutely, Steve. That's why NASA gets 6 months easily out of a massive multi-million cubic feet, zero pressure balloon into Antarctica, and they don't even have to care about leaks. It's just in the noise for lift force because of that. Like leak size in balloons, the leak sizes are very similar for all manufacturing methods. So again, like literally, the more film area, is that right? Yeah. Anyway, yes, you're correct. Night moles lost. CDF. Yeah, we'll look at this. Oh, it's a big document. Leak rate is actually very hard, and I'm very happy that they included this, because it's really hard to learn and predict how to predict leak rate and even how to measure it. So this is wonderful. Like, it took Loon years and years to perfect this to be reliable information. Thank you, Appendix. All sorts of behaviors. Interesting. Yeah. Gila, what was that? I forgot what that was. Oh, yeah, they put helium in the ballonnet at launch to launch assist, to give it a little extra oomph on ascent. These graphs were from the mission control system on Loon. That's the one where I vociferously objected to this bullshit presentation of these floating point numbers. It is like real live flight engineers have to use this for their evaluation of balloon, state. And this, the actual uncertainty of this is probably plus or minus 2 moles. So, like, you shouldn't show anything. You shouldn't even show the decimal point. It is so much of a visual distraction and brain waste of time and processing energy, misleading and possibly error-inducing crap. Don't do this on your charts, everybody. Use the proper number of significant figures to show people what matters. But anyway, the Loon software team and I didn't always get along. So fill moles, photon harvesting. Pretty. That was the New Zealand public rollout. I always love that, out of the Tekapo airport in New Zealand. Some of the prettiest pictures of the project came from that day. They had a professional, like a famous photographer, media photographer, take pictures from a helicopter for that. An engineer's life. So yeah, this is Kness, good old Kness, friends in France. What is this? So yeah, this is the Photon Harvester, the engineer, and the jacket. It's right. What it does is it just exposes your circuits to the ground and not the sky, because you lose heat via infrared, and you also receive it via infrared. And on a balloon at this altitude, when you're floating still, that's your major heat transfer method. Like, air temperature is not actually very relevant for your temperature of your objects when you're in the stratosphere. Like, Steve, down there at 30,000 feet, it's more relevant for you guys. So basically, the only source of heat at night is either power you brought along for heaters, or the Earth is losing all of its heat in the evening. You know how it gets cold at night? Well, that heat goes straight up to space. And the balloon just so happens to be between Earth and space. And if you don't have styrofoam under your ass, you can intercept that heat radiation coming up at you and use it for warmth. And you put styrofoam over the top to prevent your heat from radiating out to space. It's a brilliant idea. I don't know why nobody ever thought of it before. That was our cool thermal guy, Chad, who did that. By the way, the same guy who was granted the patent, fashionable hats for high altitude balloons. Steve, you know that patent. MPPT, that's your solar chargers, cold stuff. We'll do an episode on this. Thermal harvester. Back up. Yeah, 7 nights. ITCC. This actually happened a few weeks ago. Huh. Okay, so that's good. What next? By the way, everybody feel free to say hi in the chat, ask questions, whatever you like. You can also just chat about life in between Loon stuff.
Sup?
Alex! Welcome to the Loon info dump. I wish we had had this back then. They solved so many of the problems that were big question marks back then. There's some good stuff in here. I'm going to do a whole series of these, dive into these separate subjects. If you want to, I'm asking the chat for which one of these to do next. So far we've done the battery, the photon harvesting, and the target fill. Anything you want to see? Oh, in the meantime, we should look at the Beowulf testing video. This is the testing rig that would allow us to recreate the force of a balloon burst on the payload connector that was attached to the bottom of the balloon. And if you recall, the force of a burst horizontally was 500 Gs of acceleration for about a half second. So rather abrupt change in direction. This terrifying machine would rip the head off our payloads. I know it's probably going to be very choppy for you guys. I recommend going to find the link. Watch it yourself. You can't even see it. It's just all of a sudden there's just pieces floating through the air. Just bits and pieces. Just fucking bits and pieces. And of course this happens in the stratosphere. And like a burst is never a mode that you never initiate this, so this is always an unpredictable event. So you can't tell when or where it's going to happen, and that means your system needs to be able to take care of itself. I'm trying to find the actual ejection moment here. Needs to be able to take care of itself and not shit hard, heavy things all over the ground at some unexpected location. And it does. You can see here the piston is this brown thing, and this white, let's see if I can, yeah, okay, there you go. The white ring is the load ring at the base of the balloon, and each of these little divots here are the places where the spectra Vectran tendons would wrap around to become the valleys of the gores of the pumpkin. And here in the middle is the turbo compressor, and this is simulating a split in the side of the film on the right hand side here. Because when the split would occur, all of a sudden the 24,000 pounds of tension on the other side of the balloon would now be released. Like all of a sudden you lose all the tension here, and so now 24,000 pounds is the tension in those ropes has got to relax to release that 24,000 pounds, and so your balloon goes sideways.
Hi, I'm finally in.
Strato balloon. Is that Luis?
Yeah.
Hey Luis, it's great to have you on here. I'd love to chat more with you actually on the stream sometime if you're up for it. Just chat audio and talk. Welcome. We've been poking through all of the supplementary information. Obviously, we're looking at the Beowulf rig, the terrifying Beowulf rig, which we had over there in Moffett. There's a few incidents where the Google Health and Safety had to step in.
Seeing the Beowulf video?
Yep. I was just explaining the terrifying force here involved. Up 300 to 500 Gs applied to this poor little thing. And you can see here there's the white rod that goes down to the payload is now diagonal. And what they were testing here was what they call the mechanical fuse. And that was just a linkage in this down connector, this rod, that was designed to be much weaker than the rest of the rod above and the payload below. So that when this thing did this, when all of a sudden the top just went like this, the fuse would break. So it could go up and the payload could fall down. And because the acceleration lasted for so brief of an instant, I think half second maybe, it wouldn't move far because your balloon has a lot of inertia. It might move 3 feet, 4 feet, I think, because all the ropes are still connected. Either way, the payload didn't fall to the ground. We just simply had a shock absorbing strap that was maybe 6 to 8 feet long, a couple of meters long, with rip stitches in it for shock absorption. So this would blast that way. The mechanical fuse would break, and it would, as the Kevlar strap would tighten, it was like doubled up like this along its length. It would start trying to unroll, and there was just medium strength stitches all holding it like this. It was like a zigzag shape, and it would rip those stitches out one by one as it unrolled, and as it rips those, each one takes away some of the energy of, and it basically creates an acceleration. It spreads your acceleration over time instead of an instantaneous jerk. So it allows both the payload to start moving gradually towards that direction, and at the same time start decelerating the plate on the top. So you end up with a slow yank on both ends that doesn't tear the payload apart, and now your payload is still attached to the balloon, so the whole system can come down intact. Yeah, so you see here, we'll frame it ahead just a moment here. Yeah, terrifying speed. Up here in the front, you actually saw the mechanical fuse at one point. This was designed by John Cromie, the engineer. Very necessary testing. Very necessary. And Loon was surprised by this. We didn't expect this phenomenon.
The system was installed at Winnemucca or Palo Alto?
The mechanical fuse was part of the down connect, and that was assembled in Winnemucca. The payload shipped as a box, and the carbon fiber truss was shipped as tubes, and this down connector was shipped, as a unit, and it was all assembled and built there in the brick garage building there in Winnemucca. Yeah. I spent a lot of time in Winnemucca working on my fill system. Saw a lot of the payload shenanigans.
No, I refer at the cannon to test payloads.
Oh, I think this was at Moffett. I think this was the Moffett in Sunnyvale, at Moffett Naval Air Station there. We did a lot of testing in those hangars. Pretty sure it was there. So you can see here, there's a bunch of weights at the bottom, which represent the mass of the payload. And the mechanical fuse is one of these things down here. I'm not sure which part. Might be I think the white might be the D-spin, and the pale yellow might be the fuse. Looks like it might have been plastic. I don't know. I had other things to worry about at that point in my Loon career. I wasn't paying much attention to the payload. A giant cannon. Pretty cool. So let's go back to our list. Any requests for docs to go into? The ones we've already gone into are the battery, the schematic.
Sorry for not chat where you live, but my English talk is horrible. Thermal zones.
Oh, no worries, Luis. No worries. It's lovely to have you here. Your text is wonderful. Your text has always been wonderful. So yeah, text chat is fine. So we've done thermal zones. We'll do that one next. So Luis, what I'm going through is I'm just kind of skimming these things to see what might be interesting to do detailed future streams on, and little tweet snippets like I do of pretty pictures. My once a week tweets that I have forgotten to do for a month. Okay, so thermal zones. Thermal is fascinating on these balloons, as I know Steve and Strata Balloon know well. So let me make a note of this. Thermal zones is a must stream. It's fascinating to me. I've done a lot of research on it. The thermal experiments from the 50s and 60s are amazing. The surprising lessons they had to learn. Like on the Ghost balloon temperature sensors. I don't know if you remember, Luis, where they were trying to figure out how to measure those little fine, the hair thin beads, thermistors, how to measure without convection affecting them and things. Air density, air temperature, solar loading. Solar loading, is important because, again, as I was saying, your main heat source is radiation up there because the air is so thin. There's just not a lot of molecules of air to take heat away from you or to add it to you. So your solar and earth infrared and your radiation is what kind of drives the temperatures. Oh, there you go. DWIR, that's heat from earth. Actually, I think they have those absolutely reversed. Upwelling infrared is heat from earth, and downwelling infrared is heat from space. Logically, right? Down comes from space and up comes from earth. Actually, I think there was
inverted, yes.
Yeah, and I think Loon has had that inverted convention for a long time, and they just refused to change it. It was somebody's mistake, I think, early on, and that always bugged me because it was hard for somebody who knew the science to understand presentations and stuff, to realize everything was backwards. So Loon float altitudes, air temperatures, they get pretty cold over high thunderstorms. In the tropics, in the equatorial regions was the coldest temperatures Loon encountered because of the super tall storms clouds where the storms would reach the tropopause, and the top of your storm would be 90 degrees below zero. And even though the air in the stratosphere was negative 20 C, you basically had no heat coming from the Earth at all. Like the temperature of the heat basically that was coming up from the Earth was negative 90. And at night, that's the only heat you get. And so your balloon would get to negative 90, and that really sucked for the balloon helium because that would contract a significant amount. And that actually drove the design of the superpressure envelope, like the max pressure we had to design for, because you have to decide how low of a temperature you want to be able to survive. If you want to go to negative 90 with the balloon, that means you have to have a lot of margin above that normal operating temperature of negative 50 C. It's kind of complicated. We'll go into it another time, but Loon had to make a trade-off where basically they had to decide that, okay, at some point we've got to give up. Like statistically, it's rare that we reach negative 90, so maybe we only design for negative 80 and we try and steer around storms. So, and that's because of the material science, the limitations of the pressure of the envelope materials. Though later in the program, when they were reaching 2 to 3,000 pascals or higher in differential pressure in flight. That was much better. When we started with the IBIS balloons, when I was there, started in 2013, we were really hard pressed to reach 1,000 pascals, and that was when this was when there was no way you could hit. You could survive for -90. Solar loading, that's just heat from the sun. Thermal boundaries. Again, feel free to ask questions or clarifications, and I'll of course do more on these later. So there was electronics and hardware, hard surfaces on the top, hard surfaces below the balloon that sometimes receive sunlight through the balloon and sometimes directly from the sun. Yeah, stuff that hung outside got really cold and really hot if it was black. Yep. Photon Harvester is cool. We went over that earlier. We'll go over that in another video. Did I mark that? Yeah, I did. Battery bays. Yeah, you gotta keep stuff warm. Interesting, they broke it up into zones. Yeah, we'll go into all of this another time. Yeah, okay, so the payloads had to sit out in a parking lot while they waited for launch, and they had to sit out in that crane while they were prepped for liftoff. So you gotta prepare for that kind of stuff. And this is the one that sucked the most: humidity. I wish we, yeah, humidity is really hard to deal with. It's hard to deal with because you suddenly go to a very cold place from possibly a very wet exposure. And some of the materials on the balloon are hygroscopic, which is absorbing water vapor. And that means when they get to the stratosphere, the water vapor might cause internal pressures from ice crystals forming in materials. It may make their strength properties different. And at the most simple case, you might just get frost that is now deposited on surfaces like circuit boards. Like if you have a fairly sealed payload box with 80% humidity inside of it, it's not going to short out in Puerto Rico on the ground. But when your air inside the box goes to -40, it's frost on every surface. So you can see how it's a pain in the butt. And launching from Puerto Rico was the worst case, the jungle, where it was always humid. Yeah. Yeah, so Winnemucca was at 1,300 meters, which I'll tell a story another time about how I chased down a problem for a week that was not a problem at all. It was a factor of the fact that my vacuum gauge was reading 23 inches of vacuum, and it was reading that when I was supposed to get 29 inches. It was reading 23 because that was the ambient pressure of 1,300 meter altitude launch sites. It took me a week to figure that out with the electrical engineers from the company. Anyway, that was fun. Okay, so we'll go over the thermal zones more in detail. Request for the next section here. And if we've already done it, I'll just let you know and we'll pick another one. I will pick one if I don't hear from you. Okay, I'm picking. Let's go through zero pressure with ballast. Zero pressure and ballast are very approachable for amateurs, by the way. Well, I say that. It's approachable for amateurs who live in a region where you can carry a lot of weight and you can have a big envelope. I'm sorry to the UK guys, they can't do that. And I'm not sure if the European countries, if any of those allow it either. I think the Netherlands does. So I was looking at moving my balloon consulting to the Netherlands at one point, and it wouldn't be very useful if I couldn't launch reasonable payloads. The balloon film is so beautiful, isn't it? This is the last gen of film, the PE01. Just crystal clear. So beautiful. Like you can see in these gores, you can see the scaffolding on the end of the Moffat hangar. See this grid? That's the scaffolds in the big end door, and you can see like the big square opening. Very pretty. Actually, yeah, it looks like one door has a scaffold and the other door is present because the actual doors had these two little rows of windows, I think, on there. Yeah, they did. 2 little rows of windows. So this left half of the reflection, the arc, is the actual Moffat door, and the right door is missing with the scaffold in its place. It was during the repairs. You can see, of course, the wooden ribs of the giant airship hangar through the balloon, the brown ribs. Let's take a momentary break here. Give me a chance to go to the bathroom. You can go to the lobby and get some snacks. I will be right back if I can find the screen for be right back. By the way, I apologize if your name doesn't appear in the Patreon thank you on this next screen. I haven't updated this app in 7 or 8 months, so I will get that fixed for next stream. I just haven't been running this program. And we're back. Hope you guys had a chance to get more popcorn. Okay. Let's finish up this. Oh, this is a big one. Holy moly. Oh, 10 pages. I keep misjudging the size of the scroll bar. Okay. So you probably had a chance to read that. Super temperature is the thing I was talking about earlier. That's the swing in temperature limits how long you're going to maintain pressurization, which means if you don't maintain pressurization, you come down. So this is all right. I'm not seeing any details of how to do ballasting. This is just like what temperatures happen, which, what temperatures happen is very good data for designing balloon systems and running your calculations to determine, what your balloon should be, what you can do with balloons. Yeah, this is good. We have at least some design references for what balloon styles. By the way, reverse ballonnet plover was the best and final design. The yin yang was okay, and the yin yang is what Raven is currently supplying to the military. They are not making the reverse ballonnet, and I'm not sure if that's because they didn't get the IP or because their line isn't set up for reverse ballonnet. Stay between the lines. Yeah, this is good. We will come back and look at this. Although there's not a lot of data, there's no information on how the ballast works, but it's good to understand when you need to ballast and how much ballast. And that's with this document. That's a little bit of a weaker stream. We'll probably pair that with another topic. Zero pressure ballast. Not much here. Pair with another topic. There we go. Okay, what? Any requests for the next topic? We've done probably about 6 of them so far, I think. By the way, feel free to say hi in the chat. It's lovely to hear from you. I will pick one here if there's no suggestions. We'll wrap the stream up at the top of the hour. Let's take a look at the sizing tool.
How you to disable auto moderator. It refuses my messages.
Oh no! Yes, thank you for letting me know. Absolutely. There's no. Do you know if it's probably the Twitch auto mod? Let me pull that up. Thank you. Thank you. I'm not a pro at this, and that's very good. Twitch.tv. I'll just put I will just turn auto mod off, since I don't think people are swearing or being bad in my streams anyway. I just left it on the default setting. Can you tell if it's the Twitch auto mod or the Restream one? Takes a little while to load the Twitch page when I'm streaming. My little laptop's not the most powerful.
Auto mod.
Auto mod. I think that's Twitch. I'll just turn Restream and Twitch off. Might be Stream Elements. Oh, there's so many things hanging around. Auto mod. I know Twitch's mod stuff is turned on. Dashboard. Stream Manager. Yeah, star. I hear ya. Well, I mean, I don't hear you. Sorry, this is taking a little while.
Asterisk.
Quite. Oh, so slow. So slow. I need to quit some apps. Probably QuickTime would be good to quit.
Sorry not to help here, it's my first time in Twitch.
Oh no. I'm so sorry. Oh dear. This is hilariously repeating the word Twitch in my ear. Oh my god, I hope you don't hear this. How do I stop this? This is hilarious. Okay, we have technical difficulties. There we go. Finally, got the haha and stopped saying Twitch. Okay. Do you guys hear the text-to-speech speaking your comments out? I can't believe this is so slow. This is even slower than it should be here. I'm not running Restream.
Settings page. Moderation level.
Yeah, I'm still waiting for the Twitch dashboard to load. Oh my goodness. I'm trying to just load it on my iPad. It's taking so long. Oh. The U.S. military Navy is here in town to give air shows all weekend long. It is the Blue Angels jets making low flights all over the city. Okay, so where's settings? Oh, it's still so slow. I'll try and load it in Safari here. Dashboard.twitch. Login. I feel like Insights, settings, there we go. Come on. Log in. There we go, settings. Moderation. There we go. Come on. You can load. Thank you for helping me with that, Luis. Oh, there we go. Okay. Automod rule sets. Just turn this off. It's just like a main off button. No, but I can turn off all the custom bits. No filtering. No filtering.
Set level 0.
Yep. Filtering. No filtering. No filtering. No filtering. No filtering. Save. Let me see if there's any other settings in moderation. I do have hyperlinks blocked. Was that one that that you needed? I used to get a lot of spam hyperlinks. Followers only mode. Okay, I think that will help. I'll turn off the hyperlink block now too, just for completeness. Okay, see if that will see if that will stop being blocking.
You mentioned that Loon had a hard time with storms. How they overcome that? Perfect.
Awesome. They overcame that by simply avoiding storms in the beginning when the IBIS balloons simply could not do it. Like this, what the storms would do is it would just bring the temperature down to zero pressure, and because the balloon would be colder than most of the rest of the planet, that you had designed your minimum daily temperature to go to. So like you design your balloon to go basically in a diurnal swing of superpressures. I'm sure you probably already know some of this. So for example, IBIS used to be designed for 400 Pascal daytime a swing between a delta of like I think we started at 1200 Pascal max, and so at the beginning of the mission it would be 1200 Pascal, 800 Pascal at night, 1200 at noon. And as you lost helium, that 400 Pascal window would slowly go lower in pressure. So then you would have 10,000 Pascal at noon, and then 6,000 Pascal, or 600 Pascal, sorry, let me back up. You would have 1,000 Pascal at noon in the daytime, and then 600 Pascal at night, and it would slowly creep down closer to where night was closer to zero. But that difference between the night and zero, like we had to choose, since our balloons, the strength of the film and the design shape determined how much pressure we could max reach. We had to make sure that we never exceeded that at noon. And the distance between zero and the bottom night temperature was basically how long your system could survive leaking. But we had to choose like what is the minimum night temperature you want to survive at, because in the tropics the diurnal swing from noon to -90 C was below zero pressure, like even at the start of the mission. So you just had to not go into that temperature or accept that you would have losses in storms. And the way they resolved it was to move around storms. They added ballasters. So in an emergency, you could dump mass, which would cause you to go back up and regain pressure. But it was dangerous to use for that situation, because then it would raise your maximum noon pressure. So you couldn't drop so much mass that your maximum pressure would reach the bursting point. So that was really only effective later in the flights. And really what solved it was simply being able to operate at higher pressures, so that your maximum daily pressure was very far, so that your nighttime lowest pressure was very far from zero, so that you had a long flight ahead of you as leakage creeped that diurnal daily pressure swing window. It was a long way from zero, so you could still get lower night temperatures and not reach zero pressure. And that was the solution. Like the PE01, I think in flight, don't quote me on this, and I'm not trying to hide the information, I just don't know if I remember properly. I mean, it was like 3,000 or 4,000 pascals, I think, which is a tremendous improvement over the IBIS film, which was like 1,200 pascals. So yeah, I think that's what resolved it. And by the way, Luis, this is conversational memory from me. I can't verify some of these things. Some I remember well, but I wasn't involved in many parts of the project, just tangentially around it. So sizing, what is this? Is this interesting or not? If this is a software thing, I'm not interested. This is looking like a software thing. Oh wait, no. Okay, maybe this is a sizing piece of software to design the balloon. That would be interesting. This looks really like basic computer science 101 though. This is looking boring. Yeah. Why would they even include this? This is like standard trade space analysis of any project. Well, I mean, there's a few. Yeah, okay. Yeah, obviously. Did they actually tell you anything useful about these things? I mean, what is the envelope mass? The shell, the ropes, And the ballonnet, yeah, no kidding. Why do they call it a fin? Or is this a different balloon design? This might be a different balloon design from what I'm thinking of. Great. Yeah. I mean, it's good to know, but yeah, I mean, this is pretty basic balloon science, but it's good to teach people. You know, it takes some thinking to derive this information. So yeah, it's good to have a reference. Battery. Well, it's ridiculous math, but sure. I'm not a math person. I don't think I'm going to do a stream on this. What I can tell, it's... oh my god. Cool. Some programmer will love this. I mean, some balloon projects will need to make this program. So, nice. Cool. I mean, maybe...
One day we would talk about the politics around Loon. I recently realized the prerogatives that Peruse has on the project to permit overflight. Impressive.
Yeah, let's do that sometime. Politics was a big thing, and it always remained a big thing. I thought politics would smooth out and just become something that wasn't even thought about, but politics changes, and you know, regimes change, and yeah, we actually had fewer overflight permissions for fewer countries in the southern hemisphere than I imagined. I had thought we had the whole southern hemisphere clear, but we didn't. There was always negotiations going on. Okay, so that's boring. Probably won't come back to that. What else do we have here? Oh, well, we're about at the end of our stream, so I think we'll wrap it up there. Do you have any thoughts? I guess I can turn that red text off, right? You guys have any thoughts or questions? I am happy to answer them. We'll be back again sometime soon.
Did Google manage to reduce the Loon to 10 pounds?
Of course they did. How do you think Loon operated? The LTE antennas were 2 grams each, and they were made out of aluminum foil. No, Alex, Loon had the power to send very convincing people to the FAA to get, again, politics, to get them to work with us in terms of airspace. So
why did they need permissions?
Well, they didn't need permission so much because Google met the requirements that were hard for us to reach in 5 kilograms. Like when we did our balloons, our limit was 5.7 kilograms, the US exempt unmanned free balloon limit. And what that exempted you from was some requirements that were basically too heavy to meet in the old days for a small balloon, which includes strobes, the string, the strength of, no, that's a different issue. You had to have an aircraft transponder, you had to have dual cut-downs, redundant cut-downs. You had to be in contact with air traffic control every so often. And those things were really hard to meet in a small balloon. And cost-wise, transponders were just out of the... they weren't light enough. Like, transponder power was ridiculously high when we did our balloons, you know. There were no UAV. Well, the UAV transponders were just being made. And even then, they were like $10,000 or something. Like, aircraft transponders weighed 5 kilograms. Not 5, but they weighed a kilogram at least and needed tons of power. So anyway, Loon could easily carry the batteries, the transponders, the antennas, the strobes, and talk to ATC just fine. So yeah, they met the requirements, you know, notification and approval. So yeah. Did that answer your question? I think it did. Yeah, 12 pounds, 10 pounds. No, I think Loons at the end they were I think.
So, why did they need permission? ICAO is less than 10 pounds, isn't it?
Yeah, I'm sorry, I was being facetious. Loon's payloads were about 100 kilograms, I think, at the end. So the permission they needed was, like, they didn't have to get permission because they met all of the requirements. Like, if we had done 20-pound balloons, you know, like, what is that, 10-kilo balloons, we would have had to ask the FAA if we could fly without a transponder. And they grant that exemption, but you have to ask for that for every damn flight. And they give you a very narrow window that you can launch that flight in. So that would have been our permissions. The main permissions they had, you know, they had to negotiate for every country's overflight. And while there are, you know, there are allowances in the ICAO regs for balloon overflight without permission. They have to be explicitly for weather purposes, and I think there is a mass and size limit to those. And even if Google fit those exemptions for overflight without permission, it would not have been politically wise to be drifting around everyone's country without asking for Google. I mean, National Weather Service's international weather experiments,
Cuba,
maybe.
Venezuela, Area 51 restricted on African operations, Tanzania forbidden.
Excellent. Thank you, Luis. That's good to know. Venezuela, oh, that would have sucked, trying to operate in South America. Yeah, Area 51 was hilarious because early on, when we were launching from Chico Airport in California, in Northern California.
Lol, I had no idea that we're joking about 5 kilograms. Thanks, this was interesting to watch.
You're welcome. I'll be doing more in the coming weeks. If you subscribe to my Balloon Side Dan Twitter here, you'll get updates. Yeah, Area 51 was hilarious because launching from Northern California, sadly the winds coming off the ocean would come into the Central Valley, the San Joaquin Valley, and then come up against the Sierra Mountains. And that would kind of push some of the wind down California. Basically, you know, California is kind of diagonal, and the Sierra Mountains follow that, and so it kind of pushed the wind down that way, and then the Sierras end and you go over into Nevada. Well, what's down there, directly there over in Nevada, is Area 51. And if you manage to go north over the Sierras, east of Chico, you would often run into Fallon airspace. So Nevada is just a patchwork of fucking restricted airspace. And so we negotiated, we even hired an Air Force colonel to try and do liaison with these agencies. And we finally got whoever runs Area 51, is it CIA or somebody? I don't know. To talk to us, and they said, okay, we've determined there's a condition under which we would allow you to fly over Area 51. And we're like, great. What is it? And they're like, we require that you launch from Area 51. And we're like, And reading between the lines, I think what they meant was, we'll let you fly over Area 51 if we can tear your payloads apart and look for what they contain first. Like, as long as they can control what flies, basically, they'll let you do it. And right, so Google was like, nah, no thanks. And that's why we moved to Winnemucca, because the winds often would have the path go there, and we were often cutting balloons down in Southern California, like Death Valley area. You can probably see from this new GPS data set that someday I'll map for you. So that's when we looked for a site in Nevada that was past at least the wind predictions would take balloons most often away outside of the airspaces. And so Fallon was just like 50 miles south of Winnemucca, but the winds were always very reliably west to east. So Fallon wasn't often a problem, though we did have to coordinate with them sometimes. Yeah. So, well, cool. Well, it's the top of the hour. Guys, I've had a lot of fun, and I hope you all can come back again. Yeah, let's talk more about Loon. I'm really happy that some of it is, I can talk about it now, because it's been really cool, and I've been sad that I couldn't share it. So, take care, all. Thank you for coming in, and thank you for the people who are patrons. I apologize. I'm about to show you the end credits here. And I think some patrons aren't on there yet, and that's simply because this is the first time I've started up this streaming visuals app in 6 months. And so patrons are going to be 6 months old here. So y'all have a great day/night. Take care.
See you, Dan. Me too. It was fun.